the small signal CV. You know, the PV, the polarization versus voltage, is large signal behavior. But here, this is a small signal behavior from the CV. So in other words, at DC 0 voltage, we may have two capacitance states. So we can encode the data using the capacitance, small signal behavior. So here we have some hypothesis where we have this kind of asymmetric CV. So in one state, if we have some pinned domain that cannot flip, then after the positive sweep, if we still have some domains pointing up, then we have the green the domain wall between the adjacent domains. Then when you apply small signal stimulus, then the domain wall may move. You will have some expansion of this domain. This will induce more charges on the plate. You know, more charges on the plate could be translated to higher capacitance of the cell. And if you have another configuration, all the domains are aligned, then you do not have the domain wall motion, therefore you have less charges on the plate under the AC stimulus. So we have different capacitance states. So basically we use the capacitance to encode the data, and then we can do this charge domain computation instead of the current domain. So here the idea is to demonstrate a small scale crossbar. So we made this crossbar array 12 by 12 in our clean room with all the cross points to be a capacitor, and then we can program the capacitor in the high capacitance state, low capacitance state, and then we set up some platform to test the in-memory computing with the probe card, and you can apply multiple voltages in parallel, and then with the peripheral circuits, we can demonstrate this. So here, what we need is two phases. The first phase is still apply a vector voltage per multiple rows, but since this is a capacitor, so we will charge up the capacitor from the row, and then depending on the capacitance, high or low, we have different charges accumulated on the capacitor, and the next phase is to transfer those charges out. Then we have some op-amp here, and then the feedback capacitor. Then we can have the voltage output from the edge of the array. So here in this demonstration, the peripheral circuits are on a discrete component on the PCB board. So we have the very funky setup. And here, the output voltage will be proportional to the weighted sum and modulated by the reference capacitance. So if you compare, let's say, the resistor versus the capacitor at each cross point, the benefit of capacitor is that you only consume the energy during the transient. Let's say the rising edge, you charge up, then you pay for the energy. But then for the resistance, once you have the voltage on, then you will consume the static power all the time. So here the energy consumption will be much lower compared to the static energy in the resistor case. And also, since you have capacitors, then you do not have the slip path, IR drop, those issues. And also the capacitor, you can get rid of the transistor, you can do pure crossbar array, potentially multi-tier in the 3D stacking. So those are all the good attributes, we think, that we can do this with a capacitive array. So here from the measurement results from our test setup, we can measure the output voltage as a function of the input, let's say the unstated capacitance, and also number of the unstated capacitances, and then you see the linear behavior according to the equation. So this is some demonstration. And then, so far, we talked about the inference, but how, yeah.
So for the capacitor case, it's 2 levels, right?
Mm-hmm.
So you don't have multi-level. Is it possible?
For our first generation, our in-house sample, on-off ratio is very limited, like 1.2, so we only like 1 bit data. But recently, I have included that in our unpublished work, we have observed more than 30 on-off ratio from a different test structure. So potentially we can do multi-bit with a new design. But in the first design, this one, very simple stack, yeah, only on and off. So here, let's think about the training. So far we talked about the inference. So training requires more precision than the inference. So here for the simple MNIST data set, the idea is that we can encode the MSB using the number-data memory. But then for the LSB, because you need to update the weight anyway, so those updates mostly occur from the LSB. So we want to use some volatile memory to do the LSB. Because non-volatile memory, when you write, you still pay a lot of energy and latency for the write. So here we try to have a hybrid design. Let's say the 6-bit weight is decoupled into 2 bits in the non-volatile memory and 4 bits in the capacitor. So here this is one potential solution for the training. So let's say we still have the FE-FET, and we can have 2 bits, 4 VTH states represent the MSB. So we have 4 IDVC curve. But within each MSB, then you can have multiple LSB by charging up this node gate voltage by this charging and discharging assisted by those regular MOSFETs. So here then we can have a continuous weight in this range as a function of the voltage. And then if we need to carry the LSB into the MSB, so we just reprogram the VTH state, so we can jump from here to here in the bigger more coarse-grained steps for the MSB. So here we can equivalently achieve like 64 states, considering 2 bits in the VTH state, 4 bits in the gate voltage anode state. So here with this kind of precision, we can get some accuracy for CIFAR data set, for example. So here this could be a potential solution to the training, because training is still much more difficult for the non-volatile memory. And lastly, I will spend maybe 1 or 2 minutes on large-scale model. The reason is that if you look at the machine learning model, AI model, right, you can classify that into 2 categories. One is the image classification model, your ResNet and other network. So typically only like tens of megabytes. You can do that with R-run, FE-FET, or even S-run in the scaled node. You can do 20 megabytes, 50 megabytes, not a big problem. However, for the language model, GPT, right? Even start from the very first BERT model. It's like gigabytes, to hundreds of gigabytes. I don't know what is it. GPT-3, you see here is 175 gigabytes. I don't know the latest, the GPT-4, maybe terabytes. So there's no way that you can accelerate this model, because this model must be stored somewhere, right? This model must be stored in SSD, in your solid state drive. And then in the normal scenario, you are going to fetch the model from the SSD to the main memory, and from main memory to your GPU, CPU for the acceleration. So here we try to do some pre-processing within the SSD. So today's SSD is 3D NAND. Only 3D NAND can achieve terabyte density. So here we try to do some in-memory computing, also in the 3D NAND fabric. So we have to modify the peripheral circuits, but we can have different ways to map the model into the 3D NAND by sharing the SSL, the WL, and so on. So let's give the details. There are many ways to map the model, but we have to modify the peripheral circuits to some ADC and other digital processing circuits. And here I give the details. For 3D NAND, we also need to individually address in each cell to program the erase instead of the entire block erase. So here we have designed some virus scheme to do this, and then we verify that through the 3D netlist simulation to make sure only the selected cell will be erased and other cells could be inhibited. So here I give the details, but we try to implement the in-memory computing with the 3D NAND. Hopefully with FE-FET as the gate stack, because 3D NAND, for commercial 3D NAND, as I said, so the programming voltage is like 10 volts, 20 volts. So here it's very high energy to to program and erase. Because the voltage is so high, then when you charge up the word line, the CV square, then the energy is pretty high. So here, if you can replace the FE, the charge trap layer with the FE layer in the 3D NAND configuration, then we can potentially improve the characteristics in the SSD as well. And this is also become attractive to the industry. So for example, recently Samsung asked me, can we do some initial study to, let's say, evaluate the Ferro for the 3D NAND configuration. But I think the ultimate vision for this one is to have the heterogeneous integration, because still the 3D NAND process has the peripheral circuit in some older CMOS technology node. It's not very powerful. So here, many of the computing units, for example, ADC, adder, shift register, and so on, still need performance. So the good solution is to do those peripheral logic design in advanced logic process, for example, 7 nanometer. So we can have a separate die for those logic components, and then we can have a big model stored in the 3D NAND. Then a natural solution is to do this bonding, because this bonding has become very available from the industry nowadays. So they have, for example, TSMC has this so-called SOIC, face-to-face hybrid bonding with a bonding pitch a few micrometer. So in principle, we can have many paths between two dies, and then can do the face-to-face bonding. Therefore, we can have a 3D process and a 3D NAND process, and also the logic process in separate technology node. Then we can do the integration in the future. So this is just a proposal. So with this, I will summarize. So basically, we have discussed FEFET, and we believe that this is an emerging technology that shows some good attributes beyond what ARM and other technologies have been offering. One of the advantages is the write and read is decoupled, so we just need to engineer the write through the gate stack, and then we can program to multi-level states. But still, we have some challenges in terms of variation control, and also the individual cell programming and erase in the array setting. So we have come up with some solutions from the peripheral circuits and BIOS scheme. And also we propose a new way to do the in-memory computing, that is use the capacitive readout instead of the resistive readout. And this could provide some ultimate solution for the energy efficiency. And we have collaborated with GlobalFoundries extensively by marrying their samples, evaluate their technology, and also did some design tape-out with their platform. And in the future, I think for large AI model, I mean, the 3D NAND-based FEFET could be a potential solution for those gigabyte, terabyte model. So with this, I have to thank my collaborators, especially Professor Sumandata, Professor Asif Khan, and also the students, postdocs, worked on those projects, and all the sponsors for the Ferro program in my lab. Thank you.
Any questions?
Very nice talk. So I have two questions. So the first question is the history a fact? Is it related to the thickness of the ACO, and is it also related to the geometry of the device?
It's related to the domain-to-domain variation, which of course is a function of the device size, especially the thickness. If you shrink the thickness, then domains become smaller, and also it's a function of the fabrication process, like the linear temperature, gas flow, and so on. So we don't know how to optimize the thin film from the first principle. So it's all empirical. We try some conditions, so we measure the thin film. That's why we built up this a machine learning assisted modeling framework. So if we improve the condition of the process, then we get a new sample, and then we quickly do an imaging, and then we can predict with this new sample whether the variation would be reduced or will be enhanced. So there's no first principle to guide. So it's more empirical, and Yeah, it's a trial and error kind of approach. Yeah.
And just one quick question is, so the drain array scheme, I mean, is it a function of, I mean, does it only work for small channel devices? Or?
That's correct. So yeah. So like and also with a confined geometry, with like FDSY or 3D NAND is good because 3D NAND the channel is surrounded by the gate stack. Yeah.
So it can be used for FinFETs as well?
Yeah, FinFET as well. Yeah, as well. Yeah.
Right. Thank you.
So, like following up that, so this was very interesting, Shimei. So, is there a link from like with the machine learning model, you link the TCAT, right, and the optimal like domain configuration? Is there a link to the experiments? Like how would we achieve the most optimal configuration?
So here, the experiments we have here is the metrology data. So this is the only experiments we have. Of course, we use a TCAT to predict the IDVG characteristics.
Yes.
But we haven't validated, let's say, whether this one, if you make the real transistor with this thin film, what would be the characteristic? So there's no calibration on that. So our input is the raw data from the thin film. You do the imaging, and then you get this kind of map. And then we assume that you build the device at this location, and then you get some IDVG. Yeah.
Yeah. But can you control that location experimentally if you want to actually, like from this IDVG, let's.
Oh yeah, yes, but it's hard to, in the real fabrication, it's hard to choose from the layout, right? So
yeah.
Before the fabrication, you don't know, right? You blindly design layouts that are all regular, right? So you cannot avoid this location.
Yeah, but the materials, maybe they'll develop like fine control domains.
Yeah.
That would be great too. Any other questions?
Yeah, I have one question about the hysteresis loop. So the what makes that mini hysteresis?
So what's your question?
In the big, like in the history effect, there is like one big hysteresis
yes.
loop, and there is another like mini loop.
Yes.
There. Then what makes that mini loop there? So that mini loop. So because of that mini loop, you need to reset all the time, every time, right?
Yeah.
Then how can we? What makes that mini loop? How can we prevent that?
So the reason we want the intermediate state, so here we have the mini loop. If you only need the 1 and 0, you always operate on the largest loop. That's no problem. But if you want to go to the intermediate step, my suggestion is do not switch from the, let's say you have 4 states, right? Do not switch between those 2 middle states. You always go to the ground state and then go to the middle states to avoid the history effect. This is our suggestion. Of course, if you only need 2 states, then you only have the very up and very down state, then that's fine, no problem.
So for the multi-bit thing where you had like different levels, what exactly is like the how much of a difference in voltage is acceptable for it to be measurable? In the sense that you have variability, so a difference of 0.5 volts, then you can say, okay, then I have another bit level, or what exactly is that?
Yeah, so that's a very good question. So if you make a FET, then you measure the drain current, right? So you need to have distinguishable states. So then I would say from the drain current, from the memory window point of view, then maybe let's say you have 300 millivolts between the 2 threshold voltage, you can distinguish that. Of course, you need to tighten the distribution. So to have a gap, let's say 300 millivolts between 2 adjacent states. And actually that's a number for today's commercial NAND flash for the TLC triple level cell. The adjacent threshold voltage step is about 300 millivolts.
So can we fabricate single domain device?
Oh, that's very
minimize the
that's ideal solution. If you can only have a single domain, but then that means you only have 1 bit data. You have domains fully up and fully down. And you have a very scaled device, maybe 5 nanometer by 5 nanometer or 7 nanometer by 7 nanometer. Probably you will get single domain operation.
So this could eliminate the history effect.
That's correct, but also you are limited to 1 bit operation.
Thanks for your presentation. I want to clarify my understanding of drain gate and ask some questions. And normally in the long channel case, we can ignore the drain bias effect in the channel potential, right? So, but in the drain erase case, we use the drain bias can affect the channel potential. In other words, did you use the source channel effect to individually control the channel potential?
You can also use the source side, yes. Drain and source, I mean, it's symmetric, right? So, yeah.
So, to model this device performance, we need to use 2D Poisson equation in the channel, right?
We need to use Poisson equation?
Two-dimensional Poisson equation rather than just one dimension.
So if you have a short channel and then you have confined channel, then I think the dream model can penetrate into the channel more easily. Right? So of course when you run the TCAS, actually you have done the TCAS simulation, you can verify the potential by solving the Poisson equation in the electrostatics. So we have done the TCAS simulation to verify that.
So just you used the short channel effect, right?
Yes, you have to have short channel and the confined geometry. The channel thickness is only 10 nanometer or so.
Thank you.
So did you achieve in situ learning 3D now?
Training?
Yeah.
So far most of the discussion is on the inference. Training, the only way I think is this kind of hybrid approach, because there will be endurance problem of this FE fed as well. You can only cycle, for example, 10 to the power 6 cycles. So if you do training, each small step you also use FE fed, then your device cannot sustain too many cycles. Right? So here the idea is only when you have the LSB is by charging and discharging, so it's pure electronic, right? Charging and discharging. So then only when you accumulate certain large change, then you carry in to the MSB, then you prove it once. So this could greatly save the endurance cycles in this case.
How is retention of the effect?
The retention is kind of okay. So like months, years, and at higher temperature, maybe the degradation will be a little bit faster. So retention is not that a big problem compared to endurance. Yeah.
So is there any hope for for a FEFET? So I understand it's mostly for machine learning acceleration, but how about industry? Do they consider it as a replacement to any of the memory in the memory hierarchy?
Yeah, that's a very good question. So of course for our research we care about the in-memory computing, so that's why we did a lot of study to evaluate its potential. But for industry's roadmap, so there are two near-term applications. So the first one is of course E-flash replacement. This is what GlobalFoundries is positioning this technology for 28 and 22 nanometer to replace the E-flash, the embedded flash. Because in embedded flash, you add many masks to do the to integrate that. So here you only need one more mask for the gate stack. So here, from the cost point of view, this could be a good replacement for the E-flash. This is mostly for the microcontroller application, especially for automotive business. This is the first industrial application. This is the same value proposition for RRAM and MRAM actually. But here then the FEFET, for example, the Intel, their position is different. So they want to use Ferro, not only in the FEFET but also 1T1C, FE1. They want to use it for last level cache. So they want to have a ED1 kind of application. So they have a group working on that. And there, the engineering target is different. So they try to improve the endurance. I think Intel reported 10 to the power 12 cycles, but they sacrifice the retention. So their retention is only a few seconds or maybe minutes. But for the cache, you update the data anyway. So they just want to have an L4 cache on top of the your regular L3 SRAM cache. You have a large capacity L4 cache. So you have different engineering targets. And also Samsung, their target, and also SK Hynix, their target is even different, right? They want a 3D NAND replacement. So then we have to engineer in the FEFET with thicker ferro layer, so we can have larger memory window, we can have multi-bit operation. So that's another possible application. So as far as I know, 3 targets, right? Global Foundry, if flash replacement, Intel, last level cache, Samsung, and the SK Hynix 3D NAND.
Yeah, that's what I was wondering.
Yes, yes, but of course for us, we are looking into like in-memory computing and the neural networks, acceleration and so on. Yeah.
Yeah, I mean for academia. So for in-memory computing, how do you compare FEFET to FERAM?
FERAM is very difficult to be used for the in-memory computing because FERAM is 1T1C and it's a destructive read. So every read, you need to write it. So it's very difficult to be used for the in-memory computing. Yeah.
Any other questions?
So still, industry is not ready for in-memory computing yet?
Yeah, not yet.
It's hard to predict industry. They won't have everything right? Until they have.
So just one last question. So for the global foundries, I say that the FET is better than the MRAM.
FEFET is better than
the MRAM.
It depends. MRAM also has good attributes like longer endurance, and but of course MRAM the challenge is the current write energy is so high. The switching current density is very high, so you pass a lot of current to switch it. So from the write perspective, the energy perspective, FEFET of course will be better because it's field driven instead of current driven. The MRAM is good, I mean for endurance.
There are no other questions. We can thank the speaker one more time.